All right, let's get started. It's the top of the hour. So welcome to our regular webinar series. I'm James O'Cole, Director of System Planning at ESIG, a membership-based nonprofit organization committed to providing our members with objective information, resources, and networking opportunities in support of the energy transition. We do this through workshops, tutorials, webinars, blogs, workshops, task force activities, and producing a number of technical resource materials. In the last week or so, we've published a few reports on large loads, a report on stress testing that I would encourage you to look at on our website. So our workshops and webinars are open to everyone, so please feel free to register at any time on the ESIG website. If you're new to ESIG, I strongly encourage you to follow up with us, and you can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, and Twitter. Regarding workshops, I'll remind you and encourage you to join us next week in Tucson when we'll have our spring technical workshop. It has a great agenda and a great list of speakers, and I hope that you can join us. Please look for that information on our website as well. So before we begin, let's go over a few logistics. So please note that all the participant lines will be muted during the webinar. For the Q&A, we'll be using Slido at slido.com, and please enter the event code ESIG12, and you'll see a thumbs up button next to the questions, and that allows you to upvote some of the questions, and that helps us figure out which questions we want to address first and which ones have the most interest. So please go to slido.com, ask your questions, and use the thumbs up. I will add Slido defaults to anonymous asking of questions, but if you feel so inclined, include your name, and so we can know who's asking the questions, although that is not a requirement. We plan to reserve 10 to 15 minutes for Q&A at the end, and then we will conclude promptly at the top of the hour. A recording link will be emailed once the video file has been posted, and we'll also follow up with short responses to any unanswered questions. So diving into the topic of today. So today's webinar is focused on wide area energy assessments. Specifically, we're looking at the modeling challenges involved in evaluating reliability across very large interconnected systems rather. North America and other regions operate as highly interconnected grids, but reliability and resource adequacy planning are often done region by region. That often makes it much harder to see how risk is distributed across the border system, how much support you may or not be able to get from your neighbors, and how transmission and geographic diversity actually perform under stress. So wide area assessments are an important tool that can help fill that gap by evaluating reliability across a much larger footprint, importantly using shared assumptions about load, weather, outages, transmission, and a whole host of other big assumptions. But doing that credibly is not a particularly easy task. As the studies expand in scope, the modeling challenges grow, and that could be potentially quickly. Analysts are dealing with thousands of generators, many planning zones, and market interactions, simplifications in how you do your commitment, deliverability, transfers, market friction can materially change the results. So getting the data and assumptions lined up across load, weather, outages, and such is just as important as the model itself. So really, I think the framing that we want to use for today's discussion is why wide area assessments matter, specifically how do you do them credibly, and what modeling choices matter most once you try to scale these studies up to the level where they can actually be useful for informing planning. Our speaker today is Kevin Carden, who you hopefully are all familiar with, and he is a Chief Product Officer at PowerGEM. Before joining PowerGEM, Kevin founded Astropic Consulting, where he led the development of Sermon, which is widely used across North America and many other regions for reliability and adequacy analysis. Kevin, thank you so much for joining us. I will turn it over to you now.
James, I appreciate the invitation. I'm excited about this discussion today. We've had several similar webinars recently discussing the same topic. I'm excited about the venue today, though. ESIG brings that technical focus, and we'll get to dive into some of the details of the technical challenges associated with wide area energy assessments. I'm going to provide some kind of educational background in terms of the process that's gone into getting us to where we are today. And as Jane mentioned, some of the distinctions between how you may perform an assessment if you're looking at a single region, a single utility, a single state, a single ISO versus these wide area assessments, how they differ in terms of the scope of the analysis, the setup, some of the kind of foundational assumptions that you make that go into that. And we'll try to camp on a couple of slides to really dig into some of the foundational assumptions that go into that, but hopefully provide everybody a new perspective in terms of what kinds of information that we'll expect to get out of this, how it will weigh into decisions going forward, how it will help inform the plans, and honestly, the value that the continued individual regional level assessments will continue to provide. So with that, Brooke, let's go ahead and jump into the agenda. So the agenda today, just a handful of key points that I want to address, but I do want to, as I said, camp on some of these and really kind of dig into some of the details of what's entailed in performing these wide area assessments. First one is just kind of talking about the complexity that's involved. If we're looking at either the Western Interconnect, the Eastern Interconnect, certainly, thousands of generators, dozens and dozens of zones that have to be simulated, kind of the constraints around how you actually set up and simulate those zones, the challenge of collecting data, aligning the data, calibrating the data, all the work that that's involved there. Second step, modeling the market friction. How do we take into account resource adequacy is not just an accounting exercise. And I'm going to come back to that over and over again, that it's not as straightforward as looking at all the resources, adding up the capacity and comparing to load, even all the resources after factoring in renewable profiles and so forth. It is not as straightforward as trying to perform an accounting exercise to look at resources and how they compare to load with uncertainty. You need to take into account the way that the system actually operates. You need to factor in how are emergency operating procedures deployed, how reserve sharing arrangements affect how power flows between zones, what kind of economic constraints affect that. So we'll get into detail there. Visualizing diversity, the implications for looking at wind in the Midwest that may influence reliability in the Southeast, solar diversity, the east to west differences and how that could inform or influence the reliability from one zone to another. Load diversity, obviously important, but also understanding the correlation of load. We have these large cold weather events, and how does the correlation of cold weather across the entire Eastern Interconnect affect reliability for everyone? Outage variability. Again, we have these cold weather events. What kind of correlated outages might you expect during cold weather? How does the fuel supply, what kind of availability constraints might you have on the fuel supply? And then how do we visualize this? And again, this comes back to calibration. When we simulate these events, how do we communicate that they're realistic, that given the resources that we have, how do we gain confidence that the results of the models are realistic? And we'll talk about different reliability metrics on that front. So with that as an overview, let's jump into the first slide and start to talk about some of the challenges associated with setting up these models. So last year in 2025, PowerGEM was tasked with performing a pilot assessment, working with each of the EROs in the Eastern Interconnect and working with WEC and with ERCOT or with Texas RE to perform a wide area energy assessment. We call it an energy assessment, but it's a resource adequacy assessment. We're going to analyze both any type of capacity shortfall, any type of energy shortfall. We just make some assumptions, and I think we'll get into some of the simplifications that have to be made when performing these studies in terms of fuel supply and others. But it is a traditional resource adequacy study. You can see the topology here that we have for the Eastern Interconnect, and not zooming in here, but you get a sense for the complexity associated with performing a study for the entire Eastern Interconnect just by looking at the number of zones that we are typically contemplating for a study of that scope. Each one of these zones is committed and dispatched independently, and you have market transfers between each one of the zones. We'll talk about market friction in another slide. But ultimately, to simulate this, and again, I'll try to make the case for why you need to perform economic commitment and dispatch when performing this assessment, but it's obviously a very computationally burdensome task. Now, to compare what we did in this study versus what's done in a typical resource adequacy study, typically in a reserve margin study, an ELCC study for a utility or for an ISO, you're typically looking at just the study region plus one tie away. Now, in performing these assessments, we generally want to make the assumption that the external party is not subsidizing the reliability of the study zone. So let's say we're doing a reserve margin study for Southern Company or for Duke or for TVA. When they look at the availability of market purchases, the goal is not to say, well, this external party is long, they have excess capacity, so we can rely on that capacity to serve our needs. We don't need to build the capacity. This is the distinction of at criteria versus as found. In most of those studies, the industry best practice is to set them up at criteria. So when TVA performs a study, if a neighbor were to sell capacity, were to retire capacity, if load were to grow unexpectedly, the benefits that we get by participating in a market are limited to the diversity of weather conditions that can affect both load and renewable output, the diversity of generator performance. So those are real benefits. They should significantly impact in a well interconnected system, should impact the reliability results that you get. But we don't want another zone to subsidize the reliability of an internal zone. Now, for NERC's wide area assessment, obviously the design is a bit different. We are not trying to set a corporate plan for how much capacity to build. We're trying to assess the reliability of the grid in the near term. So for these studies, we are not having to make assumptions about the neighbors and simulating them at criteria. We are typically simulating every zone as found. So any regions that have excess, that excess will flow through in the model. Any regions with shortfalls, that could impact reliability in neighboring zones as well. One final point about that is that when you study a single region and its neighbors one tie away, if we only study one tie away, those neighbors are not going to be at criteria naturally, even if they have excess resources, because we're not modeling one tie away plus another tie away plus another tie away, which all that interaction ultimately gets that system to its target reliability. So by only modeling our study region plus one tie away, we are recognizing that that neighboring region probably needs to add capacity, or we may need to reduce load in order to get that system to the criteria. So to get that system to 1 in 10, we may have to change the load resource balance of that neighbor. And oftentimes that change may not be consistent with the effects that you're going to see as power flows from their neighbors through them to the study region that we're looking at. So I'm already starting to hit on kind of the benefits that you get from these wide area assessments of running with a wider view to understand kind of how that diversity affects all parties. All right, so kind of hit on the difference in paradigm between a zone specific or region specific resource adequacy assessment and this wide area assessment that NERC will be performing, or the EROs will be performing this year and going forward. Now, another big question here is we are simulating. So when we simulate this in Servum, we are performing the commitment and dispatch on a zonal basis. That means that every zone has perfect deliverability within that zone. And the transfer limits from that zone to the outside world are defined by a single point forecast. Typically that will be a seasonal forecast. So the transfer limit in the winter, transfer limit in the summer, but it's a fairly simplified topology from that perspective. We don't have a full network model. We're not running DC or AC power flow for this assessment. It's a transportation model. So the transfers between zones is what's used to calculate the ultimate resource adequacy. But that is still a very challenging commitment problem. So we are performing independent hourly commitment for a full week at a time in Servum. So for each zone, we look at the load resource balance. We look at the prior iterations transfers and the prices at which those transfers cleared. And we use that as an indication to build a commitment for this week that reflects when do units cycle on and off, what kind of base load generation is going to serve that, peakers, when do they operate? And then we start to get into things like emergency operating procedures and how does that interact with the neighbors? We'll talk about that in more detail when we look at market friction. But all those interactions have to be robustly considered. And so it's a very large problem. Servum does have significant advantages in being able to perform that large of a problem. We have proprietary dynamic programming algorithms that we use to perform that commitment dispatch, but it still takes about 30 minutes to run through an entire 8760 for the full Eastern Interconnect. So performing that commitment for all these zones for a full year, every generator within all those zones has a discrete operating status every hour. We are having to serve the load in every hour. We have the transfers across this entire system every hour. So it takes a significant amount of time. Now, this wide area assessment, we're not just doing it on a single year. So we are typically running 30 to 40 synthetic weather years. So when we look at a future case for this setup, we are simulating what do we think 2026 or 2027 might look like if we have the weather conditions from 1980 or 1990 or 2000, 2010. And we have built load models, so a synthetic load model that says if I have the same temperatures from July 15th, 1987 in tomorrow's system, this is what we think the load will be for each of the zones in Florida, for each of the zones in the Southeast, each in MISO. And we build that out. Everything is time synchronized, so everything's temporally coupled. So all the profiles are coming from the exact same day. So we have the historical record, the historical information for each of those to build up that data set. So we're going to simulate 40 weather years. We're also going to do forecast error. So we don't know how fast load might grow. As you're all aware, I'm sure, it's a bit of an unknown in terms of how much data center load growth we could expect in the near term. It's also a bit uncertain in terms of what the load shape might look like. So there's some uncertainty there that we try to incorporate as well. And then we also incorporate generator performance uncertainty. So outages on the generation fleet. So we are stochastically sampling generator outages. We're running that for hundreds of combinations. So we end up perhaps as many as 20,000 hourly simulations of this entire Eastern Interconnect, run that through to look at the reliability metrics for each one of the individual zones. All right, I spent a long time on that slide. I'm going to go ahead and move forward, but hopefully those concepts all make sense and provide some perspective on why it's important to pick up some of these dynamics that we look at in these wide area assessments. Market friction. When I started my career at Southern Company, and I've been doing this my entire career, close to 26, 27 years now, the challenge that I was tasked with initially was we did a post-summer review. And so after the summer of 2000 and 2001, we did a post-summer review that looked at why we had such close calls in meeting our reliability target. We had a reserve margin target, and the expectation was that we would not face any shortfalls, but we saw market prices in the several $1,000s a megawatt hour back in the early 2000s. And so we wanted to understand or explore why that was the case. So when we simulate Southern Company plus TVA plus its other neighbors, we tended to see that the the accounting suggested that we had plenty of capacity to meet the load without running into any type of scarcity condition. And I've seen this over and over again in my career, is that if you just take a simple accounting perspective on the markets, that there's typically enough reserves in the system to meet reliability. And it's not to suggest that there's any type of playing games with the system, but the rules that are in place for each one of these individual markets ultimately influences how much power flows from one zone to another. For instance, each individual balancing area has targets for the operating reserves that they maintain, and then there's some reserves beyond that. So you've got spinning reserves, regulating reserves, and we have contingency reserves, non-spinning contingency reserves that may be held as well, and then backups for that, depending on kind of how conservative the balancing area is. Also have to think about things like the temporal effects, that if I run my pump storage down to a particular pond level, then I may not have that resource for later in the day. So yes, if there was perfect coordination across the entire Eastern Interconnect and no entity had these thresholds that they impose, then perhaps more power might flow. But the realities of how you operate the grid ultimately influence what power flows. So reserve sharing agreements, where some entities may agree that if this generator fails, that you'll back me up. There may be other things as well, that I'm willing to call demand response in order to sell to this particular neighbor, but I may not for other neighbors. Those demand response resources typically have call constraints. I can't call demand response every day, 8 hours a day. So how does that influence? I have economic considerations. When we look at these data centers that supposedly are able to curtail, how often are they willing to curtail? At what kind of economic thresholds are they willing to curtail? So ultimately, we have found that those behaviors influence the transfers that actually occur between zones. And setting up the market with this economic commitment and dispatch framework allows us to calibrate our system. We think that kind of this method of performing the economic commitment and dispatch, we can replicate conditions that have happened in the past. So it allows us to get a better sense of whether our model is replicating actual behavior. Also, the reason that generators fail is it's not always just a random outage. It's probably a function of how many hours is that generator operating. So performing this commitment and dispatch allows us to replicate, oh, this generator is failing during startup. I'm more likely to have, a much higher frequency of large outages if the CT fleet is operating at a 20% capacity factor versus at a 10% capacity factor. So taking all that into account, we think that's the right approach to looking at resource adequacy. Is you need a full commitment and dispatch model to understand kind of how that works. And again, this is particularly important in this wide area, because again, you could get extremely aggressive and assume that power flows all the way from Montana down to Florida if I just look at the physical transmission constraints. All right, let's move on to the next slide. Just as an example of this, and I already kind of talked about this a bit, but two zones, so zone A with a 3 gigawatt surplus and zone B with a 2 gigawatt deficit. So zone A with its own internal resources is clearing a $65 megawatt hour market price, has some additional resources available. So we sell that generation, but some of our surplus is in a demand response product. That demand response product we're not necessarily willing to call in order to sell to the neighbor. So even though we have a system that has 1 gigawatt of total surplus, zone B may still end up in shortfall. And our modeling allows us to capture this and also to calibrate historical conditions to understand where we tend to see types of friction. Another example of this is in the past, the model suggested that we were not as aggressive as we should have been, or that in history, just by looking at purchases during critical hours. So taking these synthetic years and simulating, model suggested that we would expect much more power to flow during these critical periods, but they did not. And that ended up having to do with an effect of oil turbines not operating. Well, the oil turbines had special environmental constraints, so they actually couldn't operate that much. But if you just looked at it as a capacity resource, you didn't impose those constraints on it, then you would tend to miss that. Modeling in an economic framework, we could see where that threshold actually came in, may have been at $150 a megawatt hour. If we limit the zone's willingness to sell at $150, then it won't dip into those oil turbines, and we actually get a much better calibrated system from a resource adequacy standpoint. All right, we can move to the next slide. So diversity is a big component of this, trying to understand what value that renewable output diversity, that low diversity brings to systems across these wide geographic footprints is important. It has to be coupled with the market friction aspects that I talked about before, but ultimately this is a big driver and it can help to inform. We may see that in the individual regional assessments that the profile of imports that they get based on the way that they've modeled their neighbors at criteria, or that they've modeled their neighbors with perfect capacity additions to get them to 1 in 10, may be different than the actual flows that we would expect when we look at this wide area. So insert them because we can simulate all the individual transactions as they occur across each one of these flows. We can pick up all those dynamics and we can assess and understand the diversity. Now, what's important is when you're looking at this from a wide area, and it just emphasizes the framework that we've selected over the years, is that stochastic modeling can't be simply sampling from a data set randomly, because there are so many correlations between individual components of uncertainty. The solar, the wind, the low diversity, ultimately there are maybe negative correlations between those asset classes, but that needs to be picked up, or positive correlations between those, and those need to get picked up as well. So our approach to doing this, again, I highlighted our approach of creating 40 synthetic shapes that are all time synchronized. And ultimately using that as a guide. There are some limitations to using history as a guide. And for various studies, we have employed different ways of climate adjusting those historical profiles. But again, it's representing with tomorrow's system. So the installed capacity on wind, the installed solar capacity, the load, the customer base that we expect in the future. How do we think they would perform given the historical weather conditions? And embedding those historical correlations, the temporally matched profiles, ultimately gives you a better view of what we expect the system to look like. And it's not just that it has statistical significance. We think that there are other values to that, in that you are able to calibrate. So you can say, well, what if we have a Winter Storm Uri again? We know that that affected not just Texas, but parts of Eastern Interconnect as well. Let's go simulate Winter Storm Uri, but with 2028 system conditions. So the capacity that we have in the system in 2028, the wind, solar, the load that we expect in 28 with all the data center build out. What would happen if we have that weather condition again? And being able to reproduce that, kind of the timeline on which that occurred, allows you to calibrate. You can also go back and calibrate historical events using the historical system. And we think that's also a value in the context of how people think. People tend to think in anecdotes. So when I look at next year's system, I want to say, what's the likelihood of shedding load if we have a storm like that again? We have a really hot summer like we had in 2011 in Texas. So being able to communicate the outcomes of the model is important from that perspective as well. And so this diversity, the treatment of diversity by making sure that everything is temporally coupled, we think provides a lot of value. All right, next slide. So here's just a physical example, and these numbers are generic. I had Claude just build an example. It didn't come directly from a servo simulation. But you can start to see some of the benefits. So obviously there's diversity in load. So even when it's very hot across the Eastern Interconnect, One system may be at 107% of its expected or its forecasted peak. Another zone may be at 100% of its forecasted peak. So it is in the highest load tranche for that year, but you may still have excess because you plan with reserves that you can handle some of those extreme events. So we expect to see load diversity across all these scenarios. And we expect these wide area assessments to really give us a sense of how that load diversity contributes to providing reliability across the wide area. On the wind and solar front, obviously, we understand kind of the pattern of solar, that sun rises in the east and sets in the west. And so we have the later solar hours during the summer in the west that can share with the east. That production can avoid some of the net load peaks later in the day in the east. And then during the winter, vice versa, the earlier sun in the east can help out with issues in the west during the winter mornings. Wind output, see lots of diversity between different wind regimes across the country. So understanding the correlation between wind projects across the country, and again, having all those temporally matched up helps us to better calibrate, benchmark our systems contribution or impact from wind. Let's go ahead and jump to the next slide. So I already hit on a lot of this. So data coordination challenges. I did want to speak to a few things that we ran into last year during the pilot study. Just making sure that we did have temporal alignment, and that entails things like time zone, daylight savings time, entities store their information different ways, different conventions. So getting everything onto the same time zone could be a factor. But also thinking about things that in terms of how we do our load forecasts. So when I project a 50-50 load forecast, one entity may use the last 15 years. They may have climate adjustment embedded in that forecast. I may do the forecast for all of SPP that is a coincident forecast versus some entities do a non-coincident forecast. So how do we do the benchmarking to make sure that when I represent all the Eastern Interconnect, the load variability is fairly represented in that hourly profile that we have. Data source coordination, certainly a challenge because every entity is responsible for collecting all their generator data, the load forecast. There's lots of gross ups that happen on load forecasts and data. We look at the composition of load going forward, that yes, we've got standard residential, commercial, industrial load growth, but we also have call outs for data center load. We have call outs for EV. We have call outs for behind the meter PV. How do we disaggregate that from the historical data? So there's a lot of work that's involved in constructing a synthetic set that we believe is representative of the future. How do we tie together different vintages, assumptions, and formats that somebody developed their forecast with this limited information, somebody developed it later? How do we harmonize all of those? Certainly challenge, but close coordination with each of the EROs and with NERC has given us some confidence that the outputs that we've produced are reasonable. PowerGEM also is, we've been working on this data set for 10 plus years on all the projects that we've done, and we cover most of North America in the reliability assessments that we perform. We've been building these synthetic profiles for years, and those have been a big part of kind of what goes into the energy assessments here. All right, I got one more slide here to just talk about how do we visualize that. Again, I said that we tend to think about reliability and anecdotes. What would happen if I had the same weather conditions from a historic year? So one of the valuable additions that NERC made, Mark Olson at NERC helped us to formulate kind of the plan to construct a representation of what does it mean to have a resource adequacy scenario? What are the drivers of those shortfalls? So in Servum, we produce a representative case, a typical case. So that typical will be for each season, the hottest day of the year, the coldest day of the year, the peak load day of the year. What do we think is going to happen? So what we do in Servum is we take the 40 synthetic shapes that we have. We take the one day from each one of those 40 and we average all those together. So we end up with one composite forecast of this is what we think a summer peak might look like. Its peak is going to match the peak that we have in the forecast. The wind shape is going to match the average of those 40 shapes. The solar shape will match the average of those 40. The hydro will contribute the way that it does. The imports will be average across all of those cases, but we end up with this typical shape. And this is kind of what we plan to. Obviously, we have reserves in case things don't go as planned, but that sets the benchmark or the baseline that we use to compare. And then we can look at what happens in a 1 in 10 type condition. So in the worst case, out of a 10-year horizon, how did the system perform? We take the individual snapshot from that 1 in 10 case. We might look at a 1 in 100-year scenario, 1 in 1,000-year scenario. So from these 20,000 cases, we can choose individual snapshots and look at what the typical drivers of the shortfall are. So this is a winter day, and it shows that we have higher than expected load, roughly 5 gigawatts higher than expected load. Conventional underperformance, we had 10 plus gigawatts of underperformance from the thermal fleet or the conventional fleet. In this case, the imports actually overperformed. Storage overperformed for a period. Renewable overperformed during, you can see the renewable overperformance there in the middle of the day. That must have been solar overperforming. See, I think that's all we had from this particular day. And then where did the unserved energy occur? So we had an unserved energy event from hour 3 to hour 10. So this is a very extreme event, 20,000 megawatts of unexpected need relative to what we planned to. And this is kind of where the shortfalls ended up occurring. So these types of visuals, NERC intends to use these to help communicate kind of what these risks might look like, what's driving the risks, and help planners to get a better sense of path forward. All right, my final slide, just a summary of the takeaways here before we jump into the Q&A. Brooke, if you don't mind going to that last slide. So obviously a very challenging setup. Did have to do some work in setup to be able to simulate such a large topology, both for WEC and for the Eastern Interconnect, but validating that model with many hands that we had in the work with all the EROs helping us out, able to overcome some of those challenges. Market friction is real. I think this will be an area for deeper dive going forward, is understanding how those emergency operating procedures, how you use voltage reduction, demand response, any type of economic considerations in that commitment dispatch. It'll be important to understand and calibrate those going forward. Still a lot of work to be done in that space. The diversity across wind, solar, load, outages, critical input. We think that we have a good approach to capturing the diversity, capturing the correlation across all the asset classes. But it's still a challenge to build all that data. And ultimately, we think that it can provide a lot of input back into other processes of understanding kind of how that diversity contributes ultimately to reliability across wide footprints. And then how do we communicate this to all parties involved? What does that risk actually look like? We think there are lots of ways we're still exploring, and AI is giving us new tools to be able to compare and contrast. So we're excited about kind of what we expect to come out of the next study. With that, I think I ended right on time, James. Give us time for 15, 20 minutes of questions.
Perfect. Thank you so much, Kevin. Thank you for that great presentation, that discussion. So a couple of questions just to start us off, right? With the pilot that you've done, that is a wide area assessment, kind of two parts to this. One, how is that pilot actually going to show up in Probe or LTRA, how is that going to be different, right? And how is a true wide area energy assessment perhaps different from what we have already seen? And the other part of that is, if a region has a really good, robust RA assessment at the moment, um, how does this then complement what they're doing?
Yeah, great question. I'll try to tackle each aspect of that. You may have to remind me of individual components if I go off track here. So from the perspective of a region, so still a lot of value in performing your own assessment. We think one of the key benefits of this wide area assessment is alignment of assumptions. So the framework that's used for the entire system is all the same. We're doing the same weather years. We're studying the approach to developing the load forecast uncertainty. We have kind of consistent representation of the market. So that consistency of inputs allows you to better calibrate against your own modeling results. I do think that you'll see differences that, I pointed out at the beginning of the call as well, that kind of the underlying baseline for a study that's done on an individual region may be different in that you're studying at criterion versus as found for the neighbors, unless you do want to, if I'm doing my own study, I may need to study a wider area in order to pick up kind of the year-to-year effects of the as found system. Who's short, who's long, how's that going to influence my reliability? But for a lot of this work, you are studying your zone, one tie away, calibrating the neighbors to the criteria, which means that the profile of the contributions may look a little bit different in that. Yeah, any other aspects to that question I can address?
No, I think that covered it. And so maybe that leads into another question, right? With the smaller region, the amount of fidelity and detail that you can include in that region, right? Perhaps you will have some internal transmission constraints. Perhaps the amount of detail that you have on your generation may be different. As we start to grow the scope of the study to a much wider area, going beyond the utility zone and ISO, to getting a whole interconnect, perhaps the whole continent, it seems like you'd have to make sudden simplifications. And that's a big question mark, right? If you have to. But if you do, at what point do those abstractions and simplifications, kind of start to take away from the validity of the study itself? And are there any of those assumptions that you think are critical to keep at a higher fidelity versus others?
Yeah, we do tend to see that, modeling every individual generator is important. It's not just a portfolio of generators that or grouped by individual class ultimately that influences reliability. We think it's important to pick up the dynamics across that subcategory of generators. Some may have really poor forced outage rates, and your profile of generator outages will look very different if I just assume a homogenized portfolio that has an average E4. So even if the average E4 matches the average E4 of my unit specific, I'm going to get different reliability outcomes. So there are things like that you really just can't simplify. We think you need to model every generator specifically, independently. Every generator should have a discrete operating status every hour. So those kind of things have informed the way that we've constructed these wide area assessments. It means that there's honestly not a lot of simplifications that we make going into these studies, but I think you hit on one critical one, which is the network representation. We are typically aggregating these zones at a somewhat larger area, so you're assuming full deliverability within that zone. So Circ Southeast, perhaps we have all the zones, assuming that they are transferring power, and we're not taking into account as many of the market friction components that I talked about earlier. So those individual studies where we are looking at that in more detail, you're probably going to get more nuanced information out from that, whereas the wide area assessment with that level of aggregation, kind of different inputs, still valuable in terms of the diversity value across wider zones and so forth. And that's one we certainly see value in exploring deeper. I think going forward that will continue to push on that. The other products in the PowerGEM portfolio, so Terra, which Terra was used for the ITCS study, which identified the transfer limits between these larger zones. And we leverage a lot of that work. I think it's valuable. But digging into more detail, can we take snapshots from this work and send that to Terra to look at the actual power flow to make sure that we're accurately representing the reliability contribution?
All right, thanks. So pulling on that thread a little bit, because I think this ties to the next question that we're seeing in Slido. How are you guaranteeing that it's phrased as input capability is real and dependable in those really stressful conditions? And I'll broaden input capability to say um, support from neighbors, right? So it's both the transmission capability, the transfer capability, right? Um, but also the resources available on the other side. How are we and how are you, right, thinking about it when you're doing this wide area assessment that's real, especially because we are doing some of those simplifications, right? Assuming that the generators are deliverable, for example. And when we do the transfer analyses, right, we are, I think in the ITCS, it is simultaneous transfers. Is it just a couple of snapshots through the year, right? And then you're doing a power flow analysis. Is it over 8760? So with all of that, right, and the way we're doing this modeling, um, are there, and guarantees is a big word, of course, right? How are you, guaranteeing that those resources actually are dependable and the transfer capability is there and real?
Yeah, well, you hit on it. We don't guarantee anything in the probabilistic world, right? It's all the probability distribution. But we can represent, so we do calibrate those distributions to look at what the transfers actually look like. But I'm glad you raised the distinction here that when we perform these simulations, we're looking at both the transfer capability and the resource availability, the load resource balance on each side of the interface. And we're doing that economic clearing between those two. So I have to have both the transfer capability and the load resource balance such that enough power will be expected to flow across that path. In terms of identifying what that transfer capability is, just the transmission limit that we impose in CERVM, you're right. So the ITCS study, you're typically doing a summer peak condition, a winter peak condition. So you're trying to look at it during stress periods. And you are calculating simultaneous transfer capability. So what's the aggregated import capability of this zone, the aggregated export capability of that zone, plus individual paths across between individual zones. So it is an involved task. I mean, it's a challenging study that the TELUS group and PowerGEM worked on together to develop those assessments, but it is a single snapshot. So there will be other conditions where I have different generator outage profiles, transmission outage profiles that influence those transfers. So we do think that a valid kind of future phase of work is to take some of these stress periods and analyze more of those in those types of venues.
Great, thanks. Another question that we have is about how do you gauge load forecast volatility, particularly for data centers, right, and large loads. And maybe there's a broader question here of how do large loads impact all of this kind of analysis, right? Given the uncertainty in their growth, right, and how they ramp up, given their load profiles, right? In some cases, it can be quite flat with really high load factors. In other cases, it can actually shift temporally. It can shift geographically. And of course, the fact that it's just huge amounts of load that we're talking about that may be geographically concentrated as well. So the question is about forecast volatility, but I think there's a broader question here about large loads, right, and how they factor into an analysis like this.
Yeah, great question. You're going to hear some of my policy recommendations coming out of this. Trying to stay away, but certainly, and I'm going to make a distinction between the data center load volatility and other load volatility that we typically experience. So let me start off with the historic approach that we've taken to looking at load variability volatility. So we have typically used forecast data from individual entities, maybe ISOs or utilities, looked at their load forecasts, and then you look at the actual loads, the peak loads that occurred for those respective years, weather normalized, and we see how much do they miss the load forecast by. Sometimes we use kind of GDP forecasts and actual GDP growth and correlate that back to the load growth component of economic growth, of GDP growth. So some different kind of ways that we can tease out. We expected it to be this, but it actually ended up over here. And we can build distributions around that. And typically you're looking at a fairly modest kind of economic forecast, uncertainty bound plus or minus 4%. So load might grow 4% faster than expected in a 3-year time window. It might grow 4% slower than expected in a 3-year time window. You have a recession, it grows slower. We have a AI boom and it grows faster. So that's kind of how we've looked at it historically. The AI growth is certainly changing the game here. We have to think about this. But from my perspective, ultimately, I think there's a responsibility kind of on the data center front that those are known quantities. So I'm adding these physical systems. They should have resources that back up those individual systems. So it's not really a stochastic variable so much as if they come on, and Texas has taken this approach that if you're going to interconnect to the grid, if we end up in a scarcity situation, you have to be willing to curtail. And so until the system has adequate planning for those data center growth, there needs to be some kind of supply certainty on the other side to handle that. Or it may be some kind of interaction with in terms of economic price response or emergency operating procedure activation.
Thank you. I think we have room for a few more questions here. So there's a question here about market friction. Maybe we'll jump to that, right? And how in your modeling is market friction done differently for zones and regions that have day-ahead and real-time markets, right? So an ISO and RTO versus not. And maybe this was sparked by your conversation about your time at Southern Company. So how do you capture those two types of regions differently?
Yeah, that's a great question. And I cut my teeth on the trading floor at Southern Company when I wasn't doing resource adequacy studies. I did spend some time on there making those bilateral transactions, and they're done on an hourly basis and a daily basis, and you're trying to be as efficient as possible. You may not have as much visibility into the real time of the day ahead markets, but we are still assuming relatively efficient markets kind of in those spaces as well. I think what you do tend to see is more definitive and maybe diverse emergency operating procedures across those zones, so that not part of an ISO where they have kind of a discrete set of emergency resources. We're going to call these in these order for our own customer base, whereas maybe that's more centralized in the ISOs. And we do try to pick up those distinctions in the various modeling efforts that we perform.
All right, thank you. The question that we have here that you touched on, and I think it goes to some of the fidelity as well. Why is unit commitment necessary in an R evaluation?
Yeah, and I'll probably be preaching this one until I retire, because intuitively it feels like RA is an accounting problem. It's, hey, in an emergency, I'm going to turn everything on that I need, right? And so I don't really need to commit and dispatch resources. But a few of the things that I mentioned here, we see dramatic differences in the results based on if you do it from a must-run type approach, where we just assume that everything's going to run when it's needed, versus an economic approach. And so picking up things like this region is not going to sell out of this particular resource class in order to support its neighbor. And that's not a fault of that system. It's just the way that their balancing area rules work. I'm not going to call voltage reduction or do this. I have particular limitations on that resource class. There may be economic considerations. I've got a real-time pricing program that at certain prices, this particular set of resources or demand side programs are going to activate. So that's a part of it. There are also things like the system's changing, that over time, if I use an accounting approach, a must-run approach, I'm going to miss how the changing dynamics of the system influence reliability. So I think about it, the easiest one to kind of visualize this is with your combustion turbine fleet. Historically, before we got into this boom that we're in right now, CTs ran maybe 5% of the year. So a few hundred hours a year, CTs ran. Well, they had an operating history that said, well, their E4D was X, and maybe that was at a 3% range. What we see in performing economic commitment dispatch is now when that resource class has to operate at a 20% capacity factor, we're running 4 times as many hours. And that will translate to 4 times the aggregated level of outages across that CT fleet. So there will be many more hours where I have many more megawatts forced offline because just having to change the way that I operate that fleet. So we think that using commitment and dispatch is going to pick up on that fact. I put in a forced outage rate rather than an E4D. And so if it operates 5% of the time when needed, that just translates for a 5% capacity factor. It may only be offline 100 hours, but if it's running 2,000 hours in a year, it may be several hundred hours where that unit's offline. That's going to affect resource adequacy. We see that swinging the reserve margin by several percentage points in all the systems that we've tested that before. But it's also this calibration and communication standpoint of just taking an accounting approach. It's just difficult to look back and say, all right, let's just run last year back through the model and see how it performed. I can tell whether or not my model is performing well, even if I didn't have a reliability event. I didn't shed load last year. But my model says that I had 40 hours where the market price was above $1,000. Because I'm using an economic framework, I get that calibration, that sense of whether or not I have high fidelity. I'm mimicking the behaviors of the marketplace, and I know kind of what my shortfall risk really looks like.
All right. I love your preaching on that. We'll give you more opportunity to speak on that, Kevin.
Thanks, appreciate that. I may have to bring that up on the panel next week at the ESIG conference. Another plug for the ESIG conference in Tucson.
Thank you for the plug. Absolutely, yeah. More of Kevin next week, alongside a host of excellent speakers on a very related topic. I think we have time for maybe one last question, and there's a question about storage, which I think is good. I don't know if we have enough time to get into that. There's a question about how long the model is taking. I don't think we can get into that. Question about scenarios, which is something that we recommended in our wide area assessment. We won't get into that. So very, very briefly, when people think about wide area assessments, they might think of this as just kind of stitching together different models, right? And it's as easy as that. What have you found in practice is kind of the most challenging thing and something you didn't expect as you're just putting this wide area model together? And what's the biggest gap that we have as an industry in actually doing good wide area assessments?
Yeah, I still think there will be a lot of lessons learned this year. So we did the pilot study. It was the first one that we had done for the entire Eastern Interconnect last year. I expect new findings this year. I think we solved some important challenges or questions last year and just getting the entire model to run, to perform thousands of hourly simulations across the entire system, both in WEC and in Eastern Interconnect and in Texas. I think the coordination on the load forecasts and what those mean, the coincident, non-coincident, the timing, Central Time, Eastern Time, all the profiles. You would think that this would all be straightforward, that everything could be in central prevailing time and we could simulate it all. But fortunately, lining all those aspects up and making sure that everything is being performed on a consistent basis was just a pretty big challenge. Entities providing their forecasts. One uses the last 15 years, one uses the last 30 years. One has this view of climate change, another has a different view. And so synchronizing, harmonizing all those assumptions and getting a clean view of the future is a challenge.
All right, thank you. We are right at time, so Kevin, thank you so much again for a really great presentation, both the prepared remarks and the Q&A. We really appreciate you taking the time, and thank you to everyone on the call for joining. As I mentioned earlier, an email will go out once the recording has been posted, and if there's any questions that we didn't get to, we'll try to provide responses to that as well. Again, further information on all our webinars and meetings can be found on our website, www.esig.energy. Under events, it looks slightly different than it did 2 weeks ago. So hopefully you can get familiar with the new structure there. Again, thank you so much, Kevin. Thank you, everyone. I hope you have a good rest of your day.
Thanks for the opportunity, James. Appreciate it.
Thanks. Thank you.